Oh, this is gonna make the internet mad. The internet's already mad at me. Hello, Internet. My name is Quinn, and this is Blondihacks. I'm back on the PM Research steam engine today, and this is a very exciting day because we're going to see this engine run in a form for the first time ever in this video, so stay tuned. I'm going to finish up the valve, and we're going to mount the cylinder, tune up the steam chest a little bit. It's going to be great. Let's go. So we finally have enough parts here that I can assemble the cylinder on the frame. Now, getting this alignment right is key, and that's why I haven't drilled any other holes in the end here. A lot of people asked why I didn't drill the mounting holes for the gland and the cylinder when I set up for that hole. Well, two main reasons. One, because this hole had to be drilled from the other side, and there's no room to drill them from this side, and you can't drill all these other holes from this side because they're not in the center, so there isn't room. So there's a couple of constraints I'm working with here. I need to do this on the drill press because it's the only machine I have that has the Z height needed to drill from this side of the casting. Now I could possibly squeeze it in on the mill if I had really short drills and used collets to hold them. However, the drill sizes that I need to use for this, I don't have collets for. You know, there's a 9/64 and there's a number 50 drill. Don't have collets for any of that. So that's why I'm going to do this on the drill press, and that's why I wanted to make all of these parts first before drilling anything, because I'm going to use these parts to align everything. So there's basically three things that need to be in alignment here. The gland nut, which goes in on this side, and then the inboard head, which goes in on this side, of course. Then I also need to have the cylinder casting on there, and this needs to be rotated such that the steam chest is relatively square. Now this doesn't have to be perfect actually, because the valve free floats on the valve rod, and then the valve rod is bent into position. So even if this was a little bit crooked, it would actually still run just fine. But you know, for aesthetics, I want to get this as square as we can. However, the other key is that the center line of the inboard head and the gland also need to be really close to the center line of the piston bore, so that the piston and rod, which are concentric, run nice and concentric through all of those holes. So we've got a lot of alignment here that I want to get just right. Now what this boils down to, of course, is that, you know, there's maybe a thou of clearance on these parts inside this hole. So they're, you know, very well located in there, but not perfect. So just exaggerating here for effect, you know, I have to get them aligned in this plane as best I can. Now, these parts are bronze. The piston rod is stainless steel. So if there was misalignment here, probably it would just run in, pump a lot of oil and 30 psi into the engine, let it run, it would probably find its home. But I want to get them as good as I can. And look, I'm probably overthinking all of this, but I'm going to do it the best I can and hopefully prevent any future issues. So what this boils down to is basically order of operations for aligning things. The gland nut is kind of the least negotiable thing, if you will, because it has to be drilled from this side, and it's not clearance holes like everything else is. So what I'm going to do is I'm going to set this guy up on the drill press, probably transfer punch or match drill these holes and tap them, and that will then allow me to mount the gland nut on the other side and then mock up everything else relative to that. And then for that mock-up, I'm going to use transfer screws. I'm going to put transfer screws in the cylinder, and then I'm going to mock up everything, including the piston in the bore, make sure everything's running nice and smooth, have it clamped in position, transfer all those punch marks, and then I can go over to the drill press and I can center drill and drill them on the drill press, and that will be sufficiently precise. And again, precision is less super critical on these holes because they're all clearance holes for the mounting bolts on the cylinder. So even after they're drilled, you know, there's going to be a little bit of wiggle room in how they mount the cylinder. Now I could also just transfer punch the holes from the inboard head, and that's actually what the documentation recommends, but I'm going to try my method and see how it works because, you know, I have the transfer screws and these things are cool. I may not be able to use the mill for the operation, but I can use it for setup. So I got my angle plate on there, and I'm going to set up the casting as you've seen me do previously in this series, and this allows me to use the head of the mill with an indicator on it to make sure that this guy is set up vertically in all dimensions. Tapping that in, and a bunch more indicating and a bunch more tapping, and then we've got this guy running nice and vertical, you know, within the vibration that's in the mill head as I move it down. So now over to the drill press. I'm going to use my precision ground flat stones, courtesy of Lance Ballsy. Thank you, Lance. And I'm going to make sure there's no dings in there, and I can bring in the setup casting. And I can just use the angle plate there as kind of a hand grip, and I can do all of my operations this way. So I'm going to clamp the gland nut in there, just like I said I was going to do. This has to be done first. And then I will transfer punch those two holes. I just straighten it by eye. There's no references here. The whole part is funky curves and casting edges. So with that transfer punched, I can now deepen those punch marks using my automatic spring punch here. I'm going to tap this, and this is 256, these holes, so very, very small. These are the smallest threads on the engine, so lots and lots of care being taken here so I don't break that tap. It's a little bit nerve-wracking. Back to the bench now for a little test fit with the gland nut here, and that looks good. Transfer screws, real quick, if you haven't seen them, they're basically like tiny little punches that you can screw into a hole. So they come in a tool like this. And conveniently this set came with 6, which is how many I need. If it came with less, I could do them in batches, but the way these work is you just thread them into the hole that you're trying to match. And then the tool here has a little wrench on the end. And you can thread them into varying amounts depending on how much clearance you need. You want the pointy bit to be just a little bit proud of the surface that you're trying to match onto. So I'm going to thread the inboard head on there and maybe a little bit further in. And then the point on there is hardened, so once they're all in there, you can give it a little whack and it's going to make a little mark on the other surface, and then you can go in with a center punch and deepen them. And then Bob's your uncle, cylinder head bolt pattern successfully transferred. Back over to the mill table here because I'm going to need it for reference in a second, but I am installing the piston. I get the inboard head in there, and I'm going to position this whole assembly together and make sure the piston is running really, really well in there. And then a C-clamp is going to hold everything in place. This is the smallest clamp I have that would span this distance, unfortunately. And then a 1, 2, 3 block is going to square up the cylinder here since we're sitting on the mill table. So far, so good. And then I just tighten that C-clamp down. And then I'm going to put a little bit of hurt on the other side with the channel locks just to even it out. And that should mark everything. And as you can see, we got a pretty good mark from all but 1 or 2 of those transfer screws. So now I can deepen them all with my center punch. And then the last couple there needed a little more of a mark. I couldn't tell quite exactly where they were. I couldn't feel them with the center punch. So I reinstalled the cylinder, found the existing punch marks with the transfer screws, and then just gave a little tap tap on the corners that didn't transfer quite well enough. And then I can go back in and punch those. And now we have our punch pattern, and we can go back to the drill press. And now I can center drill those punch marks and then drill them out. Now I'm using the Mr. Pete method here, where I'm just holding the casting base by hand and allowing it to kind of float on the table, and it'll find the drill point on its own. Now, I can hear all of you furiously typing to lecture me on the safety of holding things by hand in the drill press. That really, however, depends on the ratio of the mass of the part to the size of the drill. We're talking about a very big, heavy assembly here and teeny tiny drill bits, so those drills are going to break long before anything bad happens. But obviously, if you're drilling 1/2-inch holes in steel plate, you're going to want to clamp that down. Okay, well, it's a hole pattern. Is it going to work? Who knows? We're going to find out in a little bit here. Back to the bench to do some deburring. Of course, the outsides are easy. Now the backsides, I'm using the collapsible backside deburring tool that I've shown many times on my channel before. I love this thing. Hashtag not sponsored, but I'll link to it below because every time I show this tool, I have to link to it because I love it so much. Now, moment of truth time. Let's take it down and do some test fitting. The bolt holes all line up, but a couple of the screws are a little snug, and that's to be expected because the method I used for this was, not super high precision. but these are just clearance holes. So I think I'm going to open them up a little bit just to make sure that I can get the desired alignment of the piston rod in there. Now I happen to have a reamer that was 1 thou over the size of these clearance holes, which was lucky, so I just ran them down there with the hand drill. And test fit number 2, and now all the bolts fit very nice. Everything lines up great. Very happy with that so far. The ones on the bottom are a little tricky. That took some creative screwdriver application. Now let's get the piston back in there. And that seems to be running really, really nicely in there. I can't resist. I have to try and put some compressed air in there and see what happens. So I got the nozzle on the transfer ports, and because they're wide, I have to block half of it with my finger, but I can just barely get enough of a seal to make it move. So that's pretty exciting. We'll get more of that hot steam action later, but I'm going to move on to the valve, which has this lovely little casting. I'll file that sprue off of there, and I'm going to set it up and machine the bottom. It's clamped on a casting draft angle there, so not the greatest grip here, but that's okay. All we're doing is shaving a hair off the bottom, cleaning it up. We got a really nice finish on that. Wow, you can see the numbers in the scale there. Even a blind squirrel finds a surface finish sometimes. Next I need the center so we can mill a little pocket in the bottom, so a little edge finder action there. Now to mill a square little pocket in the bottom, I'm using an end mill here that's the same radius as I want for the corner radii in this pocket. I plunge down a little sanity check, that's all working well. So now we can get some lubricant in there and I can mill a spiral pattern out of there. The spiral just ensures that we're always conventional milling and not climb milling. Now in North America we call this a 2-flute center cutting end mill, but I understand the Brits call it a slot bonnet or a lorry drill. It's nice to hear from my viewers about what the different cultures call all of the different tooling. You'll see what that pocket does here in a minute, and now I'm going to flip it over and mill the top of this thing. So I'm using an adjustable parallel to get the height exactly right. You know, I don't know how I lived before I owned adjustable parallels. I'm going to link to this set below because it's one of the most useful things I think I have in my shop these days. So there's 2 slots in the top of this thing. One is for the valve rod, and then the other one is for the cross nut. So this is a very straightforward milling operation, just cutting a slot each way with 2 different sized end mills. And the longitudinal slot is a little shallower than the cross slot. Measuring the depth is a little tricky. I'm using a gauge pin and the depth end of my caliper. As I've said many times before on this channel, generally when you're cutting a slot, you don't want to try and do it in a single width pass because you're going to end up with a slot that's a little bit oversized. You've got one side of the end mill climb cutting and the other side conventional cutting, and then the cut on the face of the end mill is tending to push the end mill to the side as it cuts, so you've got a lot of weird forces in there, so your slot ends up a couple thou oversized. In this case, that's a feature, not a bug, because the valve rod and the cross nut are both supposed to be a little bit loose in those slots. Speaking of cross nuts, we need one, so let's make one. The kit came with this little bit of square brass bar for the purpose, so let's get that set up here. This is a very simple part because the OD of it is actually just the raw stock. It doesn't have to be machined on the outside, so all I'm going to need to do here is just clean up the end of it here. A little deburr there, so I get a clean measurement, and then I just blued up and marked the center there, and I also mark the length while I'm here. I'm just lining up by eye on that mark with the center drill, and then I can center drill and drill this all the way through, tapping size for 540, which is the thread on the end of the valve rod. This is a very low precision part. As long as it threads onto the valve rod and fits loosely in the slot on the valve, it's doing its job. And then I lop that off with a hacksaw, back of the mill, clean up the other side down to my line, little deburr, and Bob's your uncle, 1 steam engine cross nut. Now, let's do a little test fit here because we have enough parts to where we can actually see the valve things. Be a valve? Valving? I don't know. What's the verb of valve? I don't know. So the cross nut goes in there, valve rod, you can see how that all fits together. Now you know I gotta put the steam chest cover back on, put some air on there, and watch what happens. Check that out. We made a tiny little air hammer. So I started on 4 psi and then it went down to 2. Runs great on 4. It's a little sluggish on 2, but you know, nothing's run in yet and there's no gaskets on anything, so it's leaking, but so far I'm very excited with how this is working. We finally have enough components here to where I can start to talk about how these steam engines actually work. So let's get into the steam chest here, and that's what this is called. You've heard me refer to this lots before, but it is called the steam chest. So the steam comes from the boiler into this guy right here. And then inside the steam chest, we have the slide valve. The slide valve is slightly counterintuitive. It's not a precision part sliding back and forth inside the steam chest here. As you can see, it's actually physically quite a bit smaller than the steam chest. And the way it works is it floats on the valve rod. So the cross nut here is actually a relatively loose fit in this slot so that it can move a little bit. And then steam pressure holds the slide valve up against the valve face. So it's self-aligning effectively. It's a very clever design, and it makes it possible to make a precision mechanism like this with relatively primitive methods. Because it's good to keep in mind that at the dawn of steam engines, the machining was not very good. They didn't have the kinds of precision that we have today. I mean, my budget hobby machine here can produce parts orders of magnitude better quality than the earliest machine tools that made steam engines of designs like this. This is roughly a model of an 1800s mill engine. But the great thing about steam engines and why they led the Industrial Revolution is because you can make them relatively poorly and they will still run. They are incredibly forgiving, not like internal combustion engines where everything has to be perfect or the thing self-destructs. Steam engines can be made very poorly, and to quote the great Emma Ritson, they always run. So really, building these engines better just makes them more efficient. They always run, but the better made the engine is, the more efficient it is. The less steam energy you're wasting sliding parts around that don't fit very well, or losing energy to leaks or things like that. So a point of pride among model engineers is how low of a pressure will your engine run on. If your engine will run on 1 or 2 psi, that's a really nicely built and run-in engine. But of course you can't build them too well either. If everything is really like super toolmaker tight, the engine will be actually losing a lot of energy to all the various frictions and things. So there's kind of a sweet spot where everything is built really well, but not so tight that it won't run in. And then once the engine runs in, it'll run very sweetly and very efficiently. But steam engines are great for hobbyists because, as I said, they always run. So maybe the first engine you build won't run on single-digit PSI, but any model engine will run on 10 or 15 PSI. So when in doubt, turn up the pressure and you can still feel good about yourself. So right now the slide valve moves quite easily, but when the boiler is attached and it's putting pressure on the valve, then it gets a little bit stiffer and it seats much better. And then these two surfaces over time are going to run in. Now let's get a look at that valve. So the valve, as you can see, has a recess on the back. And what that recess is doing is channeling steam from one port to the other here on the port face. So this big port in the center is the exhaust, and then these little side ports are the transfer ports. So steam comes into the intake, and then the slide valve is covering one pair of these valves. So the intake steam goes into the other one, and then goes to that end of the bore, and it pushes the cylinder away from that steam as it expands. And then because the valve is covering these two ports, the steam that's in this end of the bore as the piston moves over is forced out this transfer port, through the cavity in the valve, down that center port, and then out the exhaust on the bottom of the steam chest. And then there's an eccentric on the crankshaft that's moving the valve in time, so as the piston gets to the other end, the slide valve moves back and the process reverses. The intake steam now goes into this port, which is now exposed, and pushes the piston back. Now that motion of the valve rod is controlled by the eccentric. Now this is the most primitive form of valve gear. I haven't made it yet, so it's super primitive now. It's just casting, but it's only used in the very simplest of steam engine designs, so it's basically just models. When you get into locomotives, the valve gear becomes very, very complex indeed. Locomotive valve gear is the subject of thousands of patents. Something to keep in mind is that the end of a given technology is the most sophisticated point in that technology. So when we were in the 1950s and we were crossfading from steam locomotives to diesel, steam locomotives at that moment were incredibly sophisticated and incredibly efficient. In fact, during that period, steam locomotives had much better power-to-weight ratios and fuel efficiencies than diesel locomotives did. The switch to diesel was primarily motivated initially by maintenance. Steam locomotives are incredibly high maintenance and require a lot of human labor. Diesels are much simpler and easier and cheaper to keep running. And then over time, the diesels got more powerful and of course overtook steam. But on an engine like this, we just have your basic eccentric type valve gear. So this eccentric ring here is moving on the crankshaft on an eccentric, and this motion is pulling the valve rod in and out. And then you can rotate the hub of the eccentric on the crankshaft to change the timing of the valve gear to make it behave properly. As you've seen, all steam engines can be run on compressed air. You don't want to do that too long because compressed air doesn't have the oiling, lubricating, and cushioning effects that steam does. The design of these engines is very much built around live steam. So for example, at the end of each stroke of the piston, the valve timing is supposed to be set such that the intake steam is admitted a little bit earlier than you might expect, because then that steam cushions the piston when it gets to the end of the bore and causes it to decelerate nicely and then accelerate the other way again to prevent any kind of shock loads on the piston or the piston rod. So there's little details like that that live steam can do that compressed air doesn't really do properly. But the big deal is lubrication. When you're running a live steam, you're using something like this. This is a displacement lubricator. It's plumbed into the steam line, and steam gets in here, condenses into water, displaces oil out into the steam line, lubricates the internals of the engine. These don't work with compressed air, so when you're running on compressed air, the engine is running dry. And so if you're running these engines on compressed air, lubricate everything thoroughly before you start, and then don't run them too long because that oil is going to get used up. First signs of life from this engine. I'm so excited by this. And hey, if you want to help out the channel, a little bit of love on Patreon is the best way to do that. Thank you for watching, and I will see you next time.